dig it out. Okay.
Uh, Hi, yeah. So thank you everyone for being here today. We are here for a SPTC Southern Plain Transportation Centers organized workshop series. So this is the first workshop that we are having in 2023, and Southern Plain Transportation Center, as you many of you may already know, that this is a university transportation center funded by US DOT. And as a part of this center, we organize different professional development education program. We have webinar, we have workshop. We also organize other events like short courses to for our transportation professionals in Region 6 as well as in the US, the whole US. Today we are going to talk about a very interesting topic, which is handheld FTIR spectrometer as a quality control tool for determination of SBS, styrene, butadiene, styrene content in asphalt binder, and RAP content, reclaimed asphalt pavement, in plant mixes. So this is a very interesting topic as FTIR is getting more and more attention in a pavement industry for characterizing material. So today's workshop is jointly organized by the Southern Plain Transportation Center, SPTC, and also Accelerated Bridge Construction University Transportation Center, ABCUTC, in association with the Oklahoma Department of Transportation. So in this workshop actually will be like a two. We'll have two sessions. The first session will be from 10 to 11:15. The first session will cover the test method for prediction of SBS content in modified asphalt binder using a handheld FTIR spectrometer, along with a demonstration and validation. And the second session, actually, then after the first session, we'll take a break, and then the second session will start from 1. And that session will cover test methods for measuring RAP content in asphalt mixes using the same device, that means the FTIR, along with demonstration and validation involving RAP mixes from 10 different projects and 5 different asphalt plants. These sessions, this workshop is going to be presented by Dr. Wasiuddin. Dr. Wasiuddin, let me give you a very brief overview of his career, introduction of him. Dr. Wasi is a professor of civil engineering at the Louisiana Tech University. He is the holder of a Robert Hausen professorship and also serving as a graduate coordinator of civil engineering department. He is also an associate director of Southern Plain Transportation Center from the LTU side. Dr. Rossi has published more than 30 peer-reviewed journal papers and also authored more than 100 conference paper and technical reports. He also has a patent on a one-mix asphalt additive. So far, he has served on as a PI on more than 30 projects, externally funded projects, brought around 2.5 million to Louisiana Tech University since 2007. He is a member of different national and international committees such as TRB Standing Committee, ASTM Technical Committee, and also LTRC Policy Committee. As from the topic, we can imagine that his research interest is mostly on asphalt, characterizing asphalt, nano scale, and different scale from micro to nano to macro. He has covered mostly all of it. And also currently, one more interesting thing is that like he is working on a FHWA funded 3-year funded project, which is involving waste plastic. The title of that project is Improving the Compatibility of Waste Plastic and Asphalt Binder via Theoretically Justified Identification of Compatible Blend. With that, I want to give this floor to Dr. Wasi. But before, as a logistic, actually, please post your. So we will try to make this workshop a little bit different than the webinars. It will be a more interactive than the webinars that we generally have. Let's try to ask question in between. if you want to ask question, you can raise your hand or you can post it in the chat box, and I will try to communicate with Dr. Wasi, and we'll try to make it more interactive as much as we can. So thank you everyone for joining. With that, please, Dr. Wasi, go ahead and take the floor.
Yeah, thank you very much, Ashik. Although it was too long, the interaction, so thank you very much. Thank you, Michael, and thanks to Dr. Zaman also. And most importantly, thank you all who are attending this workshop and making it successful. Uh, uh, we had a project funded by Louisiana Department of Transportation and also Louisiana Transportation Research Center. The title of that project is almost the similar one. If you just add implementation of handheld FTIR spectrometer, so that will be the title of that project. And now we mentioned quality control of plant mixes and the binders. So and then that project ended in around 2020. We had the final report already published. So the results that we'll be presenting here, actually all of them were published in several conferences and journal papers. So if you have any question, or also if you want to have more details, of course, I can share you the link for the final report and also the papers that we have published. So again, thank you very much for attending this. Please feel free to ask questions anytime. In that way, it becomes very interactive, and we needs to be practical. But it's not that only I will show you a little bit about the sample or testing, but I would like to give you the background of all these, why we are saying that FTIR can be used to determine SBS content and RAP content in plant mixes. So so that will be the first part lecture, and then of course I'll show you testing. As Ashik just mentioned, that we'll be talking about the polymer content determination in the first part, and then in the afternoon we'll talk about the RAP content in plant mixes. Now, if we have time, actually, I added one more topic, which is rejuvenator identification and quantification. So that we'll discuss in the afternoon if we have time. So now the first part is the modification of asphalt binder. A little bit of background that is just because of increased loads and high volume of traffic that we have to modify our asphalt binder. The gross vehicle weight, of course, increased, and also the number of the traffic volume increased. And also with modifications and polymers, the binder properties increased. Now, there's some commonly ones, why I just mentioned SBS determination, because there are other elastomeric polymers like SBR, crown rubber, alveoli, and there are plastomeric polymers, EVA, and then there are chemicals like P polyphosphoric acid. So those are also used, and alveoli was used more commonly, and also EVA. But right now, as far as I know, that SBS is the most common, and more than 90% of binders are modified by SBS. So that's why, we would like to focus on this particular polymer. The benefits of SBS also make it very, very popular, right? So it is as overall impact on the performance of our asphalt pavement. Like, I will start with bonding strength. So if it even it increases the bonding strength between the binder and the aggregate. So that's how SBS helps. It increases stability, elasticity, reduces stiffness of the binder compared to the other modifiers. So if you add SBS, so of course, binder stiffness increases, but as we say, compared to other binders, that means SBS improves the property but does not increase the stiffness too much. shows the highest recovery on the strain in MSCR test. So that's the elastic recovery one, as I just said, but MSCR is the test that shows that SBS really performs well and reduces rotting, improves fatigue and thermal cracking resistance of the pavement. So rotting and cracking, fatigue and thermal cracking, those are the things we talk about, right? That there's serious issues in pavement. So SBS really helps in all those categories. Now, why do you need SBS content if we have the binder grade? Why do you need that? Now, there are concerns that we have observed that there segregation, it happens. So separation, it happens, separation between SBS and the binder, which is kind of, you can say, a stability issue. Not that much with some other additives or modifiers we want to use, but SBS does have some separation. And also the thermal decomposition, we like to present some results on thermal decomposition, because as you hit the binder, there may be degradation in the SBS. So we did research on that one too. So cross-linking agents and other modifiers are used by the manufacturer along with SBS to achieve the higher performance grade. So SBS can be replaced a little bit or partially by other modifiers and also with cross-linking agents. And the reason behind that, what we are saying, is the high cost of SBS polymer and also to get higher profit. So so other polymer can be cheaper. So there's the reason. So, and why SBS is a better polymer, right? Why does it do so? Why does it performs better? So we are showing you some literature that there is a, like it constitutes a macro network at lower concentration. So it's kind of a network, of course, that performs better with elasticity and cracking. And also higher multiple stress creep recovery. So we saw that it is elastic. So because SBS butadiene, so you have 70% butadiene. So of course it shows you lots of that rubber shows elastic recovery. So because it has rubber in it a lot. So that's the reason. And it shows with FTIRS and ACM that SBS also improves the aging resistance compared to EVA that we saw in one literature. So we are reporting that. So these are the reasons that SBS performs better, like its anti-aging quality and elasticity because of it is rubber. And then also it makes a good network inside the binder. Now, why are we doing this research? There is a AASHTO T302 test specifications that quantifies the peak, which is at 965 for butadiene, which is which detects the SBS amount. So in binders, so why do we need to do this research, and why do you need to develop a universal equation? The reason behind that is that AASHTO T302 uses a calibration curve. That means you have to have the polymer. You have to add the polymer that was mixed with your binder that you purchased, and also you have to develop a curve. That means when you add 2%, 3%, 4% polymer to it, how does your signal changes at wave number 965? Then test your binder that you received from the plant, which already has SBS in, and check with the calibration curve your signal of the binder that you received. Does it match with the signal of 2%, 3%, or 4% that you added laboratory, and check if binder consistently is showing equal amount of, or the required amount of SBS. So there's the process that you have to add SBS that was used in your binder and make a calibration curve, and then check your binder, is it throughout it has the same content. So But this calibration process that Astro T302 mentioned is a time-consuming process and laborious. And so we don't want to do that. So, and manufacturers does not supply because of the proprietary reasons. They will not give you the SBS that they have added to the binder. And even if the polymer is given, so you have to develop that every project that, okay, if I add this one to this binder, and then even if we collect it to the same manufacturer of the SBS or the supplier of your binder, you collect the polymer, then you have to do that project by project. And of course, polymer, we have to use that equation that develop this equation, because uh, 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 the manufacturer will not tell you. They tell you the binder grade, but is it only SBS modified, or they have added something else with SBS? So they will not specify that. So that's the reason actually that we want to know the SBS content. As I mentioned you in our previous slides, that SBS is a better 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 uh, uh, polymer or elastomer compared to others. Now, this is the Fourier transform infrared spectrometer. So, of course, I'll show you, but the reason that we use is that it is field portable, and it is non-destructive technique. You can say you can touch anything, like in this little hole here. So, and then it will give you the signal. Requires minimal sample preparation. This hole here on the it is a hole, and then there is a diamond probe inside that hole, a little bit deep from the surface, like maybe half a millimeter deep from the surface is the diamond probe. So you just touch your sample, touch your binder there, and it will give you the sample. So it just needed, there is no need to have a shape of the material and very tiny amount. The reason for FTIRS, of course, also is that you get the chemical analysis. We barely get any chemical analysis of asphalt binder. Currently in PG specifications, we don't talk about chemical compositions or anything. Recently, Sarah is getting a very saturates aromatic resins and asphaltene. So that compositional test is getting more and more popular. Actually, it's because we want to know about the binder also, but other than that, we don't have anything. So FTIR is giving us the chemical composition or chemical changes in asphalt binder as it performs in the road. So, and also that's why we used FTIR, and also why the diamond ATR sensor. The reason is that like the spectra remains unaffected, as I just mentioned here, that even if you place different amount of binder on that probe. So it's kind of very robust and has corrosion and scratching resistivity. So that actually is very good, because you'll be applying that in the field. So those are the advantages for using diamond ATR. We have also germanium ATR, which may be a good thing for black material, but we kept using diamond ATR because of its sturdiness. So there is literature. There are lots of right now. There are lots of literature on FTIR spectrometer that people are using for asphalt binder characterization, and we mentioned some of those. And those are the earlier ones that we did during the project when we did the literature search. We mentioned those. And then also, as I said, that this is one of the ones during the project that came, but almost all of them used a calibration curve. That means to know the SBS content in a binder, that in a given binder with unknown SBS content, they didn't say anything that this will perform there. They developed one a calibration curve and check that, like the Astro T01, as I mentioned on the top. So and we also looked at what type of analysis they use. They use peak method, And then they used the peak area method. Peak height and peak area are the most common methods that people use. Peak height and peak area at 965 wavelength wave number. So what we did here, so here was our idea here, that we like to develop a equation then so that we can avoid the calibration curve. We don't have to do any calibration curve. We have an equation. We just go to the field here in Louisiana or in Oklahoma or Idaho, and then we can measure the SBS content of that binder without any knowing anything about the polymer that was used and the content that was used. So what we did is that we took different base binders, we took different sources of those base binders, and we took different SBS polymer structures. And then also we added cross-linking agent, which is sulfur in our case. And then we looked at, as we change percent of SBS, how much the signal get affected because of all these variability. You know, we looked at effect of base binders and their sources, SBS structure, cross-linking agents, all those. That if that does not matter, so we don't have to make lots of calibration curve project by project if you know, we have less variability in it. So that's why effect of all those variables we wanted to check in that project. So, and then we developed a universal equation so that we can find the SBS content. So we took a big really matrix, as I said, that our variables are too many. So we took 4 binders: PG52, PG58, PG64, and PG64 for 2 different sources. As I said, that we would like to check also the differences in different sources on XPS signal. And also we said that SBS structure will be different. So we checked on radial, and we checked on linear, and then a die block. And also we said we looked at the effect of sulfur. So we added 0.5% sulfur to the radial one. And as far as we realized that time, that most commonly used one SBS is the radial one. So we used that a lot. And then different percentages. So we were very uniform on that rigor. So we added to this 52 radial to 1, 2, 3, and 4%. And then also 1, 2, and 4%. So we added to all the different binders, 4 different binders, and also different polymer structure, these 4 percentages of, and I'll very soon show how we added that. A very simple process, and many of you maybe already are using those. And then batch, by batch, what it means is that, say we added 1, 2, 3, and 4% SBS to the binder, to this binder, we not only added that just one time, like during that month, we added this 4, or that week. We also did that another time period, we added these 4 percentages to this. And then another time, I'm sorry, this is day. So this is the batch. So we added these different percentages one time, and then we added these percentages another time to see the variability and reproducibility. And same thing we did it with this one, this step binder that we added multiple times. So here you can see that these 4 binders, it becomes 7 with SBS type, and then it becomes 9 when we edit at different times at the same amount, different times, to look at the reproducibility or effect of adding any variability in while we add. So also what we did is that, say this one batch of binder, this binder has 5 different binders, this batch. So 0, 1, 2, and 1, 2, 3, and 4%. So 5 different binders. And then we check these 5 different binders one time, and then another day, and then another day. So we checked that 3 times. So if you count all these, and then same thing with this binder, we counted in different days, which is 1, 2, 3, and 4, 1, 2, 3. So you can see that in a given binder, we not only just checked once to check any variability are there. So if you count now number of days, we check these 5 binders will be like 24 different cases. So this 9 will, this 9 batch will become 24. We checked at 24 different days, let's say, but it takes more than a day to check that many samples sometimes, but we checked all these in different days. So we have 24 cases. Now, in each case, let's say one day. So here, if you count, there are 24 cases. Now, let's say one case, this case. And this one day, we checked like with this binder, this binder, this binder, and this binder, and this, and these, right? These 5 percentages. We have 5 binders during that one day. So 0%, we check 10 samples of it, because one sample, it doesn't take more than, including cleaning and everything, it takes 3 minutes or less to check the if you get proficient on that one. So we checked 10 samples. Then on this one, we check 10 samples, 10 samples, 10 samples, and 10 samples. So this one day, we check 50 samples. So 50 FTIR tests are there, because and then you check 24 cases. So 24 times 50, there will be 1200, but it's just in second day. On that one, that particular day, like we checked only 5, 5, 5, 5, 5. So we have 25. So in total, 24 times 50 is 1175, but we 1200, but we had, because of this 25, we had 1175 samples, and I will show you results of those. But also, I'm telling you now that we have much more results because we had validation tests, and also we did check the degradation. So it is much more than 1175. So now, as I said, that as we added SBS to the binder, very briefly, I'll show you. So this is our heating mantle, and this is our quart can where we have this binder. So this is the controller. So it will control the temperature of the heating mantle. So we heated the binder, and then this is our high shear mixture. So we dipped it into the quart can, and the quart can is inside the heating mantle, and we are adding SBS from the sides. In this case, powdered, but we mostly use the pellets, SBS pellets. So the mixing process, we mentioned that in many of our literature that we started with 5,000 RPM. As we started adding SBS. So from the sides, and it took us about 30 minutes. Within 30 minutes, we finished adding the SBS. Very slowly, we start adding SBS. And total, and every 30 minutes, after every 30 minutes, we increase the RPM, rotation per minute, to 8,000, and then we come back to 5,000 RPM, and we continue half an hour. So in that way, we ran for 2.5 hours. So that was our SBS mixing procedure. The reason to use the higher temperature is that so that SBS, all, if any, floating on top as you added, it goes higher, because as you increase the RPM, it kind of sucks the material from top. It kind of have a circular flow in the I don't have this diagram for that, but there is a circular flow going on as the asphalt is being mixed. So mixing temperature, with some trials, we actually maintain 170 degrees Celsius. So this is the FTIR equipment. It's about 13 inches, and this is the front. This has cover on it. We'll take off the cover, and we'll see the diamond probe. We'll attach the diamond probe, and we'll put the samples, and you can see, you cannot see it here. So this is the top where we have this 6-inch, and then there is a small panel here, screen, and it weighs about a little bit over 4 pounds. So I'll try to switch my camera and show you the uh, the uh, the SBS, sorry, the FTIR spectrometer. Here, so I stop sharing, and then me 1 second. I'm just changing my camera. So did you see the, yes, so you see that, right? So
Yeah, we
this
can
is
see it. We
the
can see it.
handheld the spectrometer. So as you can see here, so this is the, I think you can see this is the front. It has a cover on it. So we'll replace this cover with a diamond sensor. And then this is the trigger. As you can see, this is the trigger. So that is kind of the enter button. As you touch your sample, you can just trigger it, push the trigger, and then this is the battery compartment. So this is the battery compartment. You will have 4 batteries. You can use 2. You have to use 2 at a time. So and then you can see how much charge is left. It's fully charged. So and then and this is the front or the panel where you put your, right now it's saying a username, which is asphalt, and it has a password check here. And then I have to put the password. So and then it will start. It will start, mean it will go to the ready position. So and then here also you can see that this is the power button, and this is the micro USB, because it connects with your computer when you download the data with micro USB to USB. So it goes to the computer through this. So that's it's very handy. And what you can do is that I'll show you a little bit. So I took off the cover, and then I will put the I'll put the, this is the diamond probe. So this is the diamond probe. You can see a very small hole. So you put your sample, and it's very easy to clean things. So and then this is the other side. So we have different probes. If you want to change to diamond to any other, you can use that. Also, we have one that is called DR method, diffuse reflectance. In that case, using that, the plan is to use that in the road. And so that you don't have to do the mild extraction process that we do in case of wrap. You can just touch the FTIR to the ground and say that pavement, and say how much FTI, um, uh, how much wrap is there. So that type of thing, any material you touch this. So that's a different one. That's a non-contact method when we use the diffuse reflectance. But this diamond ATR, it is attenuated total reflectance. So here you have to touch actually. So this is now FTIR with them. And then you always look at here. So this one, I will use my stylus. So this is the stylus, so you can use it here. I don't think you can see it, right? Can you
We
see
cannot
what
see
it
it
reads?
completely, but the screen
Yeah.
is visible though.
Okay,
Yeah.
so it says like start, select method, create reference method, and log off. So you just have to press start, so it will start. And then so I just press start. If I press start, it will say clean the straw, clean the crystal, so it will go on. And I will show you the slides so that it's clear to you, because you cannot see anything. What you do is that, like you just use your style and press this button. So let's say it's cleaned, and then it's checking the crystal. So here, like I use this Kim wipe. It's really clean the crystals very nicely. So this type of wipe did not use, instead of using normal paper towel. In our chemistry labs, they use this type of wipes to clean is neatly. So we use that. So now it is saying that ensure contact with sample. So this is all. Now you just have to put the sample right here, and then it will collect the spectra. It will take 30 seconds. So here you can see, I think, can you see here that I have
Yeah.
a hot plate, and I have a container here. So
Yes.
what I will do is that I will use my spatula. This type of spatula I will use, and then I will take it out from this pen, and then I'll just touch it here, and it will collect the spectra. That I will come again a little later, but wanted to introduce a little bit right now. So I'll show you after we are done that you collect one sample. So this is very simple and very less time consuming than any other test that we do for asphalt. And this is a base plate and a very sturdy base plate that you can rest your FTIR while you work in the lab. You just don't have to do that that way, the way you'll do in the field. So we don't carry the base plate, of course, in the field, but we use that in the lab. So I'll share my slides again. And any question on the equipment, how it looks, and
yeah, Dr. Vasu, we have one question in the chat.
yes, please.
So how are you accounting for aging of binder during this 2.5 hour of mixing?
Well, that is a good question. And yeah, we don't use any purge in nitrogen, or we don't cover them. We don't cover the lead with a lead or anything, foil or anything. There could be some effect of that. But I think as we saw, I would ask the guest, thank you for the question. This is very important because these all make changes and everything. Let's bring this up again in the afternoon session, because afternoon session will talk all about aging, not the binder. But this comes here that as we are adding it to the binder, how much our binder signal changes. So maybe what we could do is that we can just run the mixer 2.5 hours and then check the carbonyl and sulfoxide signals and see if that is significant to to anything. So in case of like aging, we did not use SBS, or we did not add any SBS, I don't recall. So when we check the aging, actually this mixing process was not involved, first of all. And then so maybe that's why our data did not get affected with that. But in case of SBS, of course, we mix the SBS, and then I think we mix the SBS. So that, and we are not looking at the aging signal. We are looking at the SBS signal. So did I answer that question? So maybe it did not affect much our like kind of assumptions for the SBS content curve that we tried to develop, and we did. So, but in case of aging, and it did not affect much because there are lots of data, but I think we did not look at any binder that we had SBS in it. Okay.
Sure, Dr. Rossi, and we can come back to the question later, maybe in the afternoon session as well.
Please, yes, yeah, I would encourage
data
to come back with the same question, because this question may come in a different format next time. The same question. Yeah. So
thank you.
So I'll share my.
I have one more question about this equipment. So you're saying this is a completely battery operated?
Yes.
Right. So how long does that battery last?
Yes. You say it will go conveniently for 2 hours, as our session runs for until 2:15. So I had another set of battery actually inside the big cabinet here. So I'll just put in another set of cabinet. Well, one thing I can show you, you are not, I think you can look at the other screen you have that shows me. Give me 1 second.
Sure.
So if you can see the cables, so these SBS, okay, sorry, FTIR. So it has it has a kind of a option here. If you can see from this small window that where I connect this one, and then that is actually a power cable adapter. So I can use if really like if batteries are not charged, and if you are in lab access, you have access to power, you can use the cable also and directly use the cable. So of course, the handheld, you don't want to charge it by this, but they will give you one extra set of batteries that will last another 2 hours if you keep it continuously running, of course, right? So, but as I said, that the data, it does not take much time to collect the data. So if things are ready, you may not need that long because you'll be just going and traveling to the plant to collect the data.
Thank you, Dr. Wasi.
Very well. Thank you for the question, please. So this is how it looks like, and I showed you, that this is the cover. You took the cover. This is how it looks like, and just click it, and these two clips will attach it to the FTIR, the diamond sensor. And I said why diamond sense is very robust, so that and I think this is better than showing it. So here you can see the screen. So you have that start button. So you press the start button. So and then I made it very simple, going slow. And then it will automatically ask for clean the crystal. Instead of pressing this button, I showed you the trigger. You can see my FTIR, I think, in a small screen. So this is the trigger button. So you can just press the trigger, so it will move to the next screen. So and then you have to here it says clean the crystal, so you can use rubbing alcohol. That we are saying it just for but we are we use paint thinner usually to do that. It may be expensive to use that, but paint thinner is very effective, so we use that. So that's what we do. And then the system will check the crystal as you cleaned it and press the button. So it will clean the crystal. And then it will do the background checking. So background checking. So we say less than 30 seconds, but it's really less than 20 seconds or so. The software now, as I said, is just 2-3 clickings, and then you will reach in this where it said ensure the contact of the sample. As you can see, this is you are touching the FTIR with a vertical wall or something and trying to take the data, or maybe, yeah. So we can just touch, as you see in the other screen, maybe you can see my finger. So if I just press it now, it says ensure contact sample. So if I press it now with my finger, and then I click on this button, just holding it, if you see the small screen, it will start collecting data. So I pressed it, and then you see it will start, it's showing, okay, it shows something, which is live signal 0.26. So I want to go to that screen now and show you why that is saying so. It does not, okay, this is the spatula I showed you. So you take your sample and then make a good contact, just I don't see hot binder will have any effect on contact, but if you really have issues with getting good signals, you just press a little bit. I don't think any pressing is needed. So we don't see that thing. And then if there is one thing, as it was asking, that live signal 0.26, it was saying so. So then live signal means the signal strength. So the signal strength should be when I touched it with finger, it was saying 0.26. It needs to be more than 0.1. So that ensures good contact with your sample. So that's why this screen is for, and then you press it when you it just shows you it's 0.2, 0.3, 6.4. We don't reach, normally we don't reach 0.4, but that's it just needs more than 0.1. Then click again, and then this is the same thing, just click the trigger button. So this is the trigger button, and then you see the spectra there. So that's it. So if I press my finger here, and then if I press the trigger, if you can see in the small screen, so it is sampling. So I just press the trigger button, and you can see it live that it is sampling, and then it's saying analyzing data. It's already done. And then now you can see this plot. Whatever you see in my slides, you can see the same thing here. And then now you have this stylus. This is a touch screen. So if you want to focus on how it looks like, you can make a square, and you cannot see it clearly, but you can see the curve very, you can zoom in actually in a very high scale, and then see it. So this is how we collect the. So that's it. So now it's done. So you can just start another sample, but before that, like you clean that, take the asphalt out, clean it, so that later on, if it asks for cleaning, you just use the Kim wipe to make it more clean. So in the field, what you'll do, all those are in the lab. As you saw the sample, the collecting data is or testing samples is really easy. What you can do is that, go to the field, and of course, in the field, it's always easier to use a gallon can instead of a quart can or these ounce cans. And then so we use gallon cans, and we collect binder. You don't need that much. So that's for storing purpose. But you just take a spatula and put it on the FTIR. So you see there is no pressure on it. You just put a drop, just touch it. So and then whatever you see spatula is too much of the sample. So then ensure good contact. If you touch, that was ensured and touched. Collection of FTIR spectra, because now you have to press the trigger button, and then to have it. So this is how we did that in the field. So you can see that this is an easy process. So you just repeat it for, if you want to take 10 samples, the important thing is that you need to clean it, right? So that's why you have to be ready with all tools and everything, thinner and paper towels and everything that you use. So when that data is done, so now you have to transfer the data to the laptop. And Agilent, where we bought it from, they gave us this MicroLab Lite software. So you just as you connect it, and then you click on your MicroLab lab. You have to put password, of course, enter to your software. And then as you just connect the USB, I showed you, if you go to the small screen, this is the port, micro USB port. So you just connected micro USB to USB. So as you just connect it with your computer, before that, open your software. So if you open your software with password and connect with the USB cable to your computer, it will automatically ask for the synchronize the data. So synchronize means that it will copy all the data to the folder in your computer that you have been using. They also give you a laptop actually just for using this one. So it is very easy that you don't mess up with that. So it transfers the data automatically. You press synchronize yes, or maybe if you don't want to synchronize, if you want to just open it, and the software, you can look at the previous results and go there and look at. So that's how actually you collect the data, transfer the data to the laptop. Now you select your file that, go to the previous data. You saw that previous data. So you go to the previous data, and this screen will open. So select your file and press the export button. So this is the export button. So after transferring the data, you go to the previous data and press the export button. Select the file and export button. And very simple, you will it's asking for the name and the directory. Actually, a name is already given when you did that. So it's asking for the directory. So it will transfer data actually into Notepad. So you can transfer it to Excel. Actually, we said Excel file, and then from Excel you can copy it to the Notepad. So so data are being text file. The text file will be saved in the same directory that are copied into the Excel file. So from the from the text file, you copied it to the Excel. We use the Excel file actually. So in the text file, the Notepad text file, you see that the data is given like this, and then I will explain actually in my next slide that one. So as you can see here that there is this is the data you collected. So this is the data. That means you collect the data, and then from and it comes in Notepad file or the text file as you export it. So from Notepad, actually you'll put that into the from text file, you put that in the Excel, but this is how it looks like in the Notepad. So one is 1798, and then these two numbers, and this is the number of rows you have here. And then look at this one, a number of rows of these data, like the absorbance data you have. So the absorbance start from this one. This one, it goes down, continues. And then this is the highest wave number, and this is the lowest wave number, and this is the resolution. So you have collected values for 1798 times. So these are the absorption values that you have, absorption values in that 24 scans that you collect. So as you have the values at what it does not give, as you can see in the Notepad, that there is no wave numbers given. Only given is that this is the lowest wave number and this is the highest wave number. So there is a little bit of thing. You don't need to do that. The Excel file we created, it does all the action. So you don't need to do that. And or you can just follow our Excel file, or you can make your own and from the scratch. So that's what you have here, is that as you have absorbance values for that 1798, you now have to make wave number values between 3999.433 and wave number 650.420. So you have to create some interval. So between these, what you have to do from this to this, there are 1797 intervals. So how do you do that? Because in 1798 data points, you have intervals of 1797. So basically, you divide highest minus lowest. You divide that by 1791. So that means increment in your wave number. So this one and then this one less, 1.8636 less. So you just create the wave number column. So that's the ultimate objective. So because your highest wave number and lowest wave number is given, you create this one. So we created once, and that you can use forever in that Excel file. So you just, as you do another sample, you can just paste it your absorbance value, because this wave number is created. So you do this one once in lifetime of your FTIR, and that just collect and then just plug in your absorbance values. So that's it. So this is how our Excel file, this is the first sheet of that Excel file looks like. And automatically it creates this spectra, so that you know with the previous spectra you check that, okay, this looks like an asphalt, and it is working good. Now, just the data analysis part before we go to the next slide of the that explains the Excel file, the next sheet. So this will be useful both for RAP and then sorry, aging, and for SBS. So we need to explain this one. So of course we can do qualitative analysis. We don't have any question about that. There will be a new functional group that is different from the asphalt. But for quantitative analysis, we have to actually some kind of make a correlation, right? Regression, by doing is regression analysis, that okay, this height means this percent, this height means this percent. So that's the quantitative analysis, right? And what is the formula here, or the mechanism here? Of course, the Beer's law or Beer's-Lambert law, where the absorbance in peak height or peak area will be proportional to the concentration. So that means you have higher SBS concentration, the absorbance would be higher. with respect to peak height or peak area following this equation, following this law. So that's the principle here. So now the any asphalt binder you bring and check that has this signature, this fingerprint region where this is common for all asphalt binders. You will see these. So these are the wave numbers. Remember the wave numbers that we have created. So and then this is the absorbance. So it will match. And also you saw in the Excel file. So that these are the wave numbers and different types of functional groups. And then vibration of different functional groups create different wave number at different wave numbers. So you just collect the absorbance values on those wave numbers. So this is common fingerprint region for asphalt. But our interest is mainly what SBS does differently. So in case of SBS, as you see ASHTO T 302, and we found the same, that 965 wave number. And if you go to 965, you can see that additional peak is created. So this is the polybutadiene in SBS that created this peak. And this is very clear here. And also polystyrene is there, right, when we add SBS. So polystyrene is at 699. So you have another peak here. So without this, you see, normal binder would do like this. But if we superimpose the SBS binder with the normal, with the neat binder, we'll see this peak and will this peak. So as we saw from the Beer's law, this peak will be higher and higher as we add more and more binder SBS to that. So it's related to the concentration of SBS. That means how much SBS content is there. So there's the fundamental of it. Now, as we add a different percent of bind, so in case say this is live signal that we collected from like our data. So this is the normal binder. So you focused on between these very small range of wave number, small range from 910 to say 990. So you focus on that one. This the file is the absorbance data is just one column that you collected. So it's very easy to plot, and only 1798 data points, absorbance points. So it's very easy to handle. So you can see this is neat binder. So this is just 1% SBS, this line. This is 2% SBS, and this is 3% SBS. This is 3%, and this is 4% SBS. And we plotted this, and you can see that this is very easily distinguishable. This is 4%, so this one is 4%. We separated it vertically. But if you merge that vertically, then of course you will see 4% is much higher than 3%. At least very clearly distinguishable. So this is how. So flat neat binder does not show any peak on 965 and different. So the SBS quantification, so we did two things. So those are the things, it may vary, but for our research, and we found like very good repeatability and very accurate measurements of SBS content when we use these two range. That means instead of just going there 965, what is your peak height and what is the area under this curve? What curve, right? If you want to find area, you need to have a base point. So on the left, we use 924, and on the right, we use 980. 84. So from 924 to 984 we used, and our data was reproducible and data was accurate, like comparatively. So when we use this, because how we found those, we found these base value or value points when we added more and more percent of SBS. We saw that the shouldering did not pass these points actually. So that's how we said the influence of these ones are up to this. And of course, we did lots of trials when we use that. So height. Now first, we're talking about the peak height method. So this is the 965 points. So this is 965, and we measured the height. But did we measure the total height? No, because this is total height. What we did actually, because the influence of SBS is here. And also from this data, you can see that the base can get shifted vertically. So that's why we had to make this baseline. So from 924 to 984, we had a baseline. And our height, when you say peak height method, at 965, but from this baseline point to the top. So that's the absorbance top. So that's our height. So this is the height we used. And we know that height is related because of the Beer's law with the concentration, or in this case, SBS content. The peak area method is very simple. And we created Excel file. We know that if we know the height of this point and we know the height of this point, we can just use the trapezoidal rule to find the area of two different between two vertical lines, right? So that's what we used, and we found the area under this. Of course, we subtracted this area, which is the area of the baseline, and we got the area of this curve. So there's the area method. So that's why the second sheet in that Excel file that we created, first sheet has that we created, we pasted our wave absorbance value, and also we have our wave numbers, right? Wave numbers we have in the second sheet, we have more. That means we have to create the baseline value, and we have to create the area. So this is the area between two lines, say first two lines, vertical lines, these are the area, and then second 2 points, this is the area, third first 2 points, second 2 points, this is the area, these 2 points, this is the area. So this is how we calculate it. Now I will show you a little bit on how we did that. So let's go to that. This everyone knows, and if you look at data, you can calculate now, right? So what we did at peak height, so we have this wave number 965.38, and we have the absorbance at that point. So value at right, like 84, and then on the left side it was at 924. We said that we are taking value between these 2 points, and absorbance value you collected. So at this wave number, your absorbance this, at this wave number, your absorbance this, at this wave number, your absorbance this. This is the polybutadiene area. So what you do, you just we have 4 data, x1, x2, y1, y1, y2, and x1, x2. You calculate your m, and of course you calculate your c. So we have the baseline equation. When we have these data points, that means you have x1, y1, you have x2, y2. So you have the m value, and you have the c value. So that means you have your line. So when you have your line, actually what you did is that when you have your line equation, when you have your line equation, actually you can calculate that what is your baseline value at 965. So this is your x1. So what is your this is your y1, right? Because at x1, what is your y1, the baseline value? Because the equation m and c, y equals to mx plus c, is for this baseline. So you calculate your y. So when you have that y value, and then you have your height value, you take this y, and then you get the height value. So this is your absorbance. So spectra gives you this one, the FTIR gives you this value at 965. At 65, FTIR give you this value, which is this one. At 965, it gives you this value. And then your baseline height at 965 is this one, which is 0.058. So this one minus this one is your net height. So this is the height. So I'm sorry I took too much time on this one. Similarly, actually, you can calculate the area. So because two vertical height will give you the area, trapezoidal rule another area. So you just collect the area. And also there is some negative, because maybe we got a too far. You'll see sometimes 1 or 2 negative value, but very little area. You can neglect that one. So that's why we just collect the positive area. So that's not much anything significant. So now we'll show you different scenarios. Different scenarios here, we use different binders, right? Different binders. I showed you 52, 60, 58, 64, 2 sources of 64. But here just showing 1 source. And then you see that that as we do 3 different binders, three different binders, these three different colors, and then as we added SBS, what we are showing here is that your R square value, that means with percent, it varies. Sorry, it correlates that 0.999799. So no matter what binder we use, it correlates very well. And then here you can see another binder. This binder is 64 minus 22 plus radial, and we added different percent of SBS in it, and we tested at different days. We can see that the correlation is very good based on the signal, based on the method we followed, area, and in this case height method we followed, absorbance height. So it really correlates with percent of SBS correlates with the absorbance height really well. Here we have another binder, a different one, where we use sulfur. So we can see that even when we added sulfur, actually it correlates. One is 0.969, the other one is 0.983. So you can see that these curves are not necessarily going through the zero. So in our equation, it shows that. And also I say that baseline has, need binder has some signal. So our equation that we'll develop is not y equals to mx. So let's see. So look at the different types of binder. We are radial, die block, and linear, and also different day. When we checked different day means the same binder, we checked at different days. So we found this correlation for radial, and then correlation is 0.978. And then 0.994, this case of really radial die block polymer we took, the correlation with percent is very strong. And also when you use linear SBS at different days, the correlation for with different percentages and absorbance height is very strong. So we get better relationship with height. Now, these are all the 24 cases, right? We had 24 different cases, including different days, right? We have 24 different cases. Each day on an we tested 50 samples, let's say, each day, because sometimes we go into the next day, but our, like project range is very big. So 24 cases, 24 times, and each day 50 samples were checked. So this is case 1, 24 case. So there are 50 binders. How 50 binders? 0%. 50 samples, 0, 1, 2, 3, 4%. So these are all the results, not the previous slide just shows some, like the scatter things. But this is 99, and then lowest relationship we got at 0.94, 94 maybe, and on a bad day. And then here you can see 0.94 another. And then the highest we got up to 1.00. So that means it maintains really good relationship. So the correlationship is with SBS and the index that we used, which is absorbance height, it is very good in all 24 equations. Sorry. Now the equation that we have developed using all those, we can see that like the peak height, which is the height, right? Y is our height, as you saw in all this equation, absorbance height. So this height equals to this times the SBS concentration in percent plus the C. I said that there is some C left. So this is the equation with outlier, and this is the equation without outlier. So this is the equation without outlier that I'll show you a little bit on this one. What is the R square for those. So now let's look at some results actually. What I want to show you now is that I showed you that with all these 24 different cases, it works. That means it has good correlation with percent of binder. But what we would like to see that that does say 1% height for 1% for one binder, and then you can take another out of those 24 cases, 1% SBS content. What is the absorbance height? Does that match? So we did not do that one yet. We just saw that each of those 24 cases follow the relationship with the absorbance height and SBS content, but we did not match with one another into that 24 cases. So this one will show a little bit effect of PG binder grade. That means the PG binder grade, when there is no SBS, in that these 3 different PG binders, and the signal is like this. The peak height at 965 is this. And then when you add 1% SBS to this binder, and this binder, the height is this. So now we are comparing, we are doing the parallel checking. So here you can see that it does not vary much. Same thing for 2%. We check this way vertically. We checked vertically, right? Earlier relationship 0, 1, 2, 3, 4, but we didn't check horizontally. So as you can see now that it changes significantly as we add, and they don't vary too much. They don't vary too much actually between different binders. So this is what we would like to show you here. Also, the bar is little more, but still the average, if you do this one and this one, you'll see that the 1% difference, it is kind of maintaining this. When we added the cross-linking agent, which is sulfur, and can say that binder and radial SBS. So this is 0%, but when we added with 1% SBS plus 0.5% sulfur, it did not change. So of course, sulfur improves the stability or the storage ability significantly, but it does not change your SBS polybutadiene signal. Here, there is no big change, and no big change. It's very comparable if you look at the standard deviation. So, and this is standard deviation. The error bars are in standard deviation. So the cross-linking agent also, we saw that it does not change. SBS polymer structure. Now you can see that we used one binder, but with different SBS polymer structure. That means we use 0% radial, linear, and die block. So 1% SBS, as long as it is SBS, radial, linear, and die block, it did not change much our absorption height. So this case, same thing, this case, same thing, and this case, same. So there are significant difference between 1% than between radial, linear, and die blocks. So we didn't see much difference here. And our samples, with 10 samples, right? In each case, we check 10 samples. So standard deviation based on that. Data collection at different days, of course, you saw that, you see that there is no, like there is no difference. Check parallel horizontally, so there is no difference. There's no difference here at all, almost here now. So so different days it does not. So so we checked any different binder. So what I'm saying is that any polymer structure I take, adding sulfur or not, what binder grade I use, 1% SBS signal is constant. It does not change. 1% SBS height in our case, whatever the limitations we have, sample we have, like the material source we have, it did not change. PG binder grade from different sources. So if 64 we had Louisiana and North Carolina. We use this North Carolina because it has like this asphaltene content is much lower than what we use actually in our boards. So here you can see that the difference is small. It's not significant compared to percentage SBS. This big so by the source it does not very much. At SBS mixing in 2 different batches. By batch we mean that we mixed all the different percentage again with the binder. So you can see that this batch 1, batch 2, sorry, this is 0. Batch 1, batch 2, batch 1, batch 2, batch 1, batch 2. It does not make much difference with respect to SBS content. So we did this plot to combine all the 24 different cases, and we did not like kind of whatever SBS content for 1% we plot it here 2%, 3%, 4%, and we can see that it the average we can have a very good relationship here, which is 0.93. So that's what it shows. So 0.93 if we combine 1175 data points, but we followed one method and we took out, which is Cook's distance. We took out 39 data points from there, and then we call them outliers. And when we took out 39 data points from this one, rest of the data we plotted, and it looks like this. looks like this, and our correlation got improved to 0.97, and we continued with 0.97. So here the data, all the 1175 minus 39 data points are here, and it shows a very good correlation. So with that 0.97, we actually we proceeded with that. So now the variability evaluation, that means when we have multiple operators, how does this data? So these are the additional tests that we did after that 1175 data points. So these are the additional tests that we did, and I will show you the variability. Let's look at this one. So we have A, B, C, D, 4 different operator of including cleaning and running that. So, and then whatever the way that person collects the absorbance data, not making much contact, but that's not anything significant, I say. So this yes means that already it included in that 1175 minus 39 samples. So we used that equation. So the actual SBS, of course, was 4%, and we used operator A, and that person predicted it is 4.2% using the equation, the second equation, which is without the outliers, 0.97 R squared. And operator B, we gave the same binder to operator B, and then that operator had detected that the SBS content is 3.0, whereas the actual added is 3%. So, and then so there is no error on this one. Now, we have, created more samples. Okay, this is new SBS added binder. Now check that one, what percent was added. So this is kind of the that we so this is not included. These data points are in the regression analysis. So A, B, C, D, and in that case, actual space was 4, 3.5, 2 and 2, and the prediction was 4, 4, 3.4, 3.5, 2.22, and 2.22. So we thought that this is important and this is significantly accurate. So we continued with this equation, and we did further analysis, and we did field implementation also. So now we went to the field actually. So as you can see, that field means like completely unknown binders that we have not added SBS ourselves. So we have local plant, but not always that they know the SBS content every day. So we ask them that it's proprietary, so they don't get the information. Well, so we have used also multiple operators A, B, and C in all these cases. And also we have source another. So this is Arkansas and this is Nevada. We requested friends like you that, okay, you whether you add SBS or you know the SBS content, send us some binder, don't tell us the SBS content, and we will let you know the SBS content. So that's how the process was done. And then we checked SBS, predict SBS 1.1, but there is an unknown 1.8. It was unknown. We never could check actually. From 2.2, we were told that they could not say accurately. They said 1 to 3%. We predicted 2.1. They said between 1.5 to 3%. So this is with the known people that we try to get some data and SBS content known so that we can check the variability. In this case, we were sent samples. We checked. We found that it's 1.9%, and we checked it's 2.1%. And the actual person SBS that the person later on informed us was 2%, and in this case 2%. So we also put this 95% because we are data. We have 10 samples, like 95% confidence level upper and lower. So that was our chances. Confidence interval, so 2.2, 2.1. This one was very, very little gap, right? 0.1 with 95% confidence interval. So data was good, and then it was so there were two different. Not that these are two different binders. It's not one binder, although the SBS content was same. The person says that I will not tell you, but it's not the same binder. So although it happened to be that added same amount of binder, but our prediction was this much, and we let them know that this is the SBS we have found content. Nevada one, we predicted 3.2 and 4.2, and then with the information we have is 3% or less and more than 3%. So obviously we said 4% or 4.2%. We just we went to 1 decimal point actually, because we used equation, and that's how it works. So this is our the way we can did some field implementation, that okay, the equation that we used, we just take sample data and plug in that Excel file. And then Excel file, I told you that I would like to go back a little bit with the Excel file, because it has remember the Excel file that we have created. You don't have to do anything here. You don't have to do anything. It automatically, the first file, the first page, when you put your absorbance data, when you paste your absorbance data in the first sheet of the Excel file, when you put it here, it plots automatically, and it calculates everything automatically in this file. So you don't have to do any of this processing. And in your case, if you build this, it will be the same. You don't have to do. But the first Excel sheet, just copy those 1798 points, paste it there, and then it will automatically calculate, and it will show even this height, that this is your peak height. So so that's it. So this is how we did it, and we did the field implementation. Now I have 7 minutes left, so I just have few more slides. I will continue, or I can wait for questions. I will put it on the moderator, because we can use 7 minutes for the main thing is done with the SBS.
Yeah, okay, yeah. Thank you, Dr. Rossi. That was very informative session actually, and it's good to see that like the FTIR predictions are working very good. I have one question. I think the rest of the presentation we can discuss in our next session probably. Let's give our audience a little breathing room, and also I know that you may need some breathing room too. One question I have here in our chat box is, did you consider peak area or peak intensity for your analysis?
Yes.
I-
Yeah. Okay. Continue. Sorry.
Yeah, no, that's the question.
Well, we did peak height, and also we did peak area. We found, like the difference, all those we did. I want to show you that R square. Yeah, this one. So this is like comparison with respect to that. Okay, these are the R square in 24 cases for peak height. What is the R square of the 24 cases of the peak area? And then let's find the average R square, which is the better R square, right? So this is how we kind of took that off. But our software calculates peak area. So if you want to follow that, so you can do that. But this is what we used, peak height method, and then our equation was on the absorbance at the peak, which is 965. Because for SBS, it is like that peak height really did excellent. But one thing here I would like to that's the if you go to the when please attend the afternoon session, you will see that we will switch to peak area in case of aging. So we'll quickly switch to peak area. That's the afternoon session. So that's a very valid question. But in this case, when you average this 24 R square, let's say it is 0.986, and then R square of the area, I don't remember, but let's say that's 0.983. So instead of taking 983, you will take 0.988. So it's simply like that. So it was, but area method is very accurate also. Yeah.
I'm sorry about that. I was muted. So I have got another question. From what I remember, Astro T302 used the ratio between 965 centimeter and 1375 centimeter for the percent polymer. But the calibration curve may be specific to a binder to polymer ratio, binder to polymer combination. Is this method with area under the peak not sensitive to binder to polymer selection?
Yes, like as at the end, you saw that we necessarily did not just added the all the like three different types of polymer structure, which is linear, radial, diagonal. We just didn't add those two and developed and really check that how the are the data the too scattered and the R square reduces significantly. We did not do that. So we just added all the 24 cases together, and then our like the correlation really increases because we have lots of data now that's heavy on the without the variations in polymer. But as we saw different scenarios of radial one, there was one chart for sure I showed you that like radial, linear, and die block, and we did not see much. First of all, correlates very well with different percentages. So we did not use the 39-20, the other in this case. But for, as I'm saying you, for afternoon session, because the only reason here is that it was not sensitive, we found good correlation with this area method and without using the ratio with other like with you're saying polymer concentration. So we did not see any changes here. Just butadiene signal is enough. Now, in this project, of course, I did not, that's a 2.5-year project. And then we purchased this FTI using that project too. That cost us 50,000. I think price is much cheaper. We did lots of analysis. My point is that we also developed equation using just polystyrene signal also. So that we have also. So we have other process in case this in case say you collect the same binder, same data, but you take SPS content with butadiene, SBS content with polystyrene, and then you compare like how does that data vary, right? And which signal is more, like you collected 10 samples. You don't have to do again. You can check which one has less variability in your, like in your SBS prediction is 4.1 and between 4.1 and 4.6, and the butadiene is saying no, it's 4.3 to 4.4. So maybe butadiene would be more consistent. So we did more analysis, but we found this one to be very reliable. So I'm just presenting the one that we recommended. So I have not included those slides, but we checked with polystyrene, and also we did not use any area or height ratio, but that can of course be checked. And we checked some. We found this is very reliable, and our reliability level was based on the R square when we combine the data. That's very good question. Maybe more research could be done. Which one relates it more, right? But as you say, that level of accuracy is, it's saying 4.1, 4.2, and it is maybe 4%. So we are not going out like even 0.5% of the binder SBS. SBS is added like 4% or 3%. We are predicting very close to 4% or 3%. So that we found that for the time that we had, we found that this is that we can go with. So we chose that.
Yeah.
Thank you. So of course more things
we got another question on the similar one. So not requiring a calibration curve for a specific binder to polymer combination would be a great improvement. This would make the test useful for a blind test for quality assurance testing. I think this is just not a question. This is kind of like a
thank you. Yeah, we do. As I said, the title of this project was just adding implementation of. So like it was very practical, and it was like it's we are highly confident on this one that it can predict. Now of course, I'd like to one last point that there could be, and the previous, the person who had that question too, with that index, selecting the index. So there could, we have a limited factorial, right? The polymer that we could collect. We had just used two sources of polymer. One is I can mention, I don't think they have any problem, Milagro, and one is Paragon Argon. So those two sources. So there can be variations in polymer. And then I showed the polymer that you used, our like styrene butadiene ratio. It was very close. And then so say somebody makes a polymer that has really high, unusually high butadiene in it. So of course, like the percent, like say we use 31 69 ratio and somebody use like 40-60 ratio. So SBS content determination will be off by maybe 0.6% or so, right? So so those will add variability, but the SBS that we used, there needs to be a market analysis, somehow in one data base that these are the common types of SBS being used. We source two polymer source, and we thought that this is most commonly used. And also when you applied that in the field, it shows that it kind of match with the not very unusual percent of cells. We did not get like 6% SBS content. So we would have questioned our method if in the field implementation we would have got 6% or 10% SBS. That means there is something wrong with the ratio or the polymer structure, something different. So we did not see that. But as I said, this study is limited to the materials we have tested, two different sources of SBS. And also, but binder wise, I'm confident that we cover very wide variability in binder, and the SBS peak 965 is not affected. I can hear you. Yeah.
Oh, I'm sorry.
No,
Yeah, thank you, Dr. Wasi, for the nice presentation, and thanks to our audience for being here. So I think let's take a break, and we'll come back at 1. And for our next session, we are going to discuss about test methods for measuring RAP content in asphalt mixes using FTIR with demonstration and validation involving RAP mixes from 10 different projects and 5 different asphalt plants. So please join the afternoon session at 1 p.m. And if you want to just keep logged in, you can do that too. But we'll be back at 1. Thank you, Dr. Wasi, for
thank you all very
1 p.m.
much.
Central Time.
Thank you all very much. Please come back.